back.
We
Damn,
can
see
now
what's
see
going
you.
on. Oh, okay.
And also we have the ability to switch between the lecture slide and the whiteboard fluidly in our Zooms.
Oh, okay. Okay. So actually, today is just only gonna be focusing on lecture slide. You get what I mean?
Okay.
Yeah. So I'm gonna share that again, and you're just gonna confirm. Give me 1 second, figuring it out. So can you confirm if you are seeing my lecture slide now, right?
Yes, we can see you.
Okay, thank you so much. I want to welcome everyone to my lecture today. Of course, we are still on working on time series analysis. This is going to be the sixth time that we're going to meet on over this topic. Today, I want to walk you through another interesting time series module that we call MA modules. Okay, the MA modules is actually called moving average modus. Okay, of course, before now, okay, I've walked you through what I call the autoregressive model. Okay, I've walked you through autoregressive model. Okay, and today we're going to be focusing on moving average model. I think I'm going to tell you what make the moving average model to be significant, and I'm going to tell you the reason why at times, you know, our autoregressive model cannot give us what we want. Okay, at times, and where we need to look beyond autoregressive. Okay, now uh, I'm going to go into the moving average model now. Okay, I'm going to start with the model specification. But let me tell you this. Before I go into the model specification, I think I will need to first have a recap so that, on the autoregressive models, okay, and so that you'll be able to know the difference between autoregressive model and the moving average model. Let me tell you this. Okay, by autoregressive model, we believe that the past is actually a replica of the future. That's what we mean. We believe that there's a connection between what happened in the past and what happened now. Does that make sense? That's what we mean by autoregressive. So the when I talk about autoregressive model of order one, okay, by autoregressive model of order one, I'm actually relating the current value of the series, okay, to the immediate preceding past. If I'm talking about a regressive model of order two, it means I'm relating the current value of the series, to the two previous paths. I can continue to go all the way. So, which is more or less like autoregressive model is trying to tell you past as a way to explain what is happening now. That is what we mean by autoregressive. But let me tell you this. In 2008, I want to believe, you heard about global financial crisis, right? Okay, do you know that the year prior to 2008, okay, autoregressive model assure everybody in the world that things was going to fine in 2008 because the autoregressive made them to realize that what happened prior to 2008 is still what is going to happen in 2008. Okay, which means they get it wrong. Okay, so and that was why I actually said most investors, they were not aware of the risk. okay, that was posed by, there's something that we call a large portfolios of mortgage back security, okay, large portfolios, okay, of mortgage, let me see, of mortgage backed security, okay. So actually, the autoregressive model, uh, you know, uh, did not really alerted investors prior to 2008 that there was going to be a financial crisis. Okay, you know, because the autoregressive model that they use on that, on for United States financial stock actually predicted that, of course, in 2008 is basically going to be a normal year. But we all know what 2008 turned out to be. That was a global financial crisis in 2008. Okay, which actually indicate that autoregressive model has misled us. Does that make sense now? Okay, it is not all the time that autoregressive model can actually capture market situations. Now, let me tell you this: in a country or companies where they are actually experiencing a rapid growth or advancing technological development, of course, the autoregressive model cannot work in that kind of situation, because when you are experiencing a rapid advancing technological innovations, you don't expect your economy to actually look like, or your productive capacity to look exactly or look very close to what has happened in the past. Okay, and that is what led us to what we want to do today. There are times, instead of relating the current to the past, we can just relate the current to residuals in the past residuals. Okay, I'm going to say that again. The autoregressive model actually relates the current to the past, but the moving average model will relate the current value of the series to the previous residuals. Okay, I'm going to give you, I'm going to give you the model now. This is the, give me 1 second. Uh, this is the model specification. If you look at the model specification now, okay, if you look at the model specification now, you basically going to see, I'm talking about this guy, okay. Now you have a YT, right? The YT is the current value of the series. What is WT? The WT is a current residual. WT minus 1 is the pair, the preceding, the immediate past residual, and so on like that. Okay, these are residuals are what economists are going to, they normally call shocks. Okay, so another specification of moving average model, okay, is so which means if you take a look at what I'm displaying now, okay, this is more or less like our predictor variables here. They are the past white noises. WT minus 1, WT minus 2, they are white noises. WT is a current white noise. WT minus 1 is a immediate one. Okay, so take a look at this now. And of course, WT follow normal distribution with a mean of 0 and the variance sigma squared. Okay, so that is the specification that I just talked about. Okay, now the feeder model is now going to be this guy. Can you see that VTEP model? Just like the same way that we did in our autoregressive model, we actually have a two-way to specify that. I remember I specify, the population model, and I also specify the feeder model. Okay, so you can see the difference between the moving average model and the autoregressive model now. Why the moving average model puts into consideration, trying the past when you want to explain the current. Okay, but the moving average model does not do that. What moving average model is relating the current, to the past, to the current and the past residuals. That we actually call the white noises. Okay, so you can see that now. So also I said the feeder model, the feeder MA models use the past residual to predict future value of the time series. Maybe if they have used this this model prior to 2008, okay, maybe that would have alerted investors. Okay, that would have alerted investors. Okay, so take a look at that. So the autoregressive model that was used was actually wrong. Okay, the autoregressive model is trying to say the future actually resemble the past. That is what autoregressive means. The future resemble the past. But we all know 2008 does not resemble the prior years. You get what I mean? So we get it wrong. And one thing in the world is the reason why we got different kind of models. Okay, maybe there's a problem with one model. A model has misled us. So what we are going to do is actually to look beyond the model and actually apply the model that makes sense. Okay, intuition. For a time series of consumer price index, if economic conditions cause a larger than expected increase in the CPI, okay, which is a large positive noise, we might expect the CPI of next month to be above what is expected. Does that make sense? So, which means the future will no longer resemble the past, because what you are actually going to expect will be more than what you have been expecting. That is no longer autoregressive in nature. Does that make sense now? And that is why the idea of the moving average model basically going to come in. Okay, and then we can look at the moving average in another context. Okay, in another context, there's something that we call the moving average. I'm not talking about moving average model now, where you actually added, like for instance, you relate the current to the past, like 3 previous past. Okay, YT minus 1, and you find the average. Okay, we call this moving average, not moving average model, but just moving average. Okay, we just wanted to take notes of that so that you don't confuse moving average. This is like moving average in another context, not in the context that we're seeing it right now. Okay, now this is looking like what? ARO for that 3, right? Is that not looking like ARO for that 3? Because I actually relate the current to the 3 previous pass. That's an ARO for that 3. Okay, but let me tell you this: the MA of order Q model does not have past observation. Does that make sense? The MA model, we don't consider past. There's no connection between the past and the current. We're actually going to relate. The only relationship in the moving average model is to relate, the current to the current residual and the past residual. Does that make sense? Okay. Now, just like the way we look at autoregressive model of order 1, we also want to look at the MA of order 1. In the MA of order 1, this is the model specification. Okay, the model specification in is basically what you're seeing now in the population form and in the feeder form. All you're seeing here is just relating the current value of the time series with the current noise and the immediate past noise. The WT is the current noise. The one investor economists, they're going to call current shock. Okay, shock. This guy here, shock. Okay, shock. Right? Does that make sense? Okay, the current shock, WT, is a current shock. WT minus 1 is the immediate past shock. Okay, so this is MA1. Okay, now, the other time under the AR1, we have properly, right? Like we look at the theoretical mean, right? The theoretical variance and the theoretical autocorrelation, right? We also want to do the same here. Okay, I want to look at it properly now. Take a look at all of that. Okay, the theoretical mean, the expected value of YT equal to mu, The variance of YT, if YT follow moving average model of order 1, okay, if the YT follow moving average model of order 1, the expected value of YT is going to be mu. The variance of YT is going to be sigma squared into 1 plus A1 squared. This is different from the one we had under the autoregressive model of order 1. And let me tell you this. The autocorrelation at lag 1 is A1 divided by 1 plus A1 squared. But you know what? In a situation where the lag value is greater than 1, the autocorrelation is going to be 0. If what I'm trying to say, if I'm talking about, but that is not the same with the AR1. You know, when we're considering the AR1, right? The autocorrelation, we can determine the autocorrelation at lag 1, at lag 2, at lag 3, and so on like that for for AR1. You know that, right? But for the moving average of order 1, we cannot. We can only get the autocorrelation for lag 1, and anything other than lag 1 is going to be 0 for moving average model of order 1. Please take notes. Okay, so if you take a look at this guy now, give me 1 second. If you take a look at this guy now, okay, that implies the variance of a YT that follow a moving average model of order 1 will be greater than the variance of a white noise. Because take a look at this. The variance of a white noise is sigma squared W multiplied by this guy. Automatically, the variance of YT will be greater because of the fact that A1 squared, the entity here is going to be greater than 1. Does that make sense? So in MA of order 1 model, okay, the variance of the YT that follow MA of order 1 model, okay, will basically be greater than the variance of the white noise. I just wanted to take note of that. Okay, like I said, these are properties of moving average model of order 1. So what is the takeaway here? Since the ACF plot show the estimated autocorrelation at different lag, ACF plot for a time series generated from MA1 model cut off after lag 1. Now I want you to listen carefully. I need you to listen now. Under the when we're dealing with the autocorrelation, when we're dealing with the autoregressive model, okay, what happened in the autoregressive model? In the autoregressive model, when you generate the autocorrelation function plot, it decreases when K increases, right? And the partial autocorrelation, for instance, if I'm talking about autoregressive model of order 1, the partial autocorrelation will cut off after lag 1, right? For the autoregressive model of order 1. Okay. Now I need you to pay attention now. When we are dealing with the autoregressive model, autocorrelation function decay exponentially to 0. The partial autocorrelation cut off at a lag K, but the reverse is the case under the MA model. Under the MA model, you know what happened? Under the MA model, the autocorrelation function cut off at a particular lag for the MA model. What cut off at a particular lag for the AR? What cut off at a particular lag for the AR is a partial autocorrelation function plot. Does that make sense? For the AR, okay? In AR, in autoregressive model, autocorrelation, the ACF decay to 0. Why the partial autocorrelation cut off at a lag. But in the case of a moving average, the reverse is the case. In the case of a moving average, what happened? The autocorrelation in the moving average will cut off at a particular lag, while the partial autocorrelation of the MA decreases as lag. Does that make sense to you now? The reverse is the case. Now take a look at this. It means if I want to identify whether a model is an MA1, because we can have MA1, MA2, MA3. If I want to identify within the class of the MA model, I'm going to use ACF plots. because the ACF plot, okay, ACF plot for a time series generated from MA1 cut off after lag 1. Okay, that was what you see here. If you take a look at here, we said for k greater than 1, for k greater than 1, what is going to happen? Okay, the autocorrelation function will be 0 for k greater than 1. You can only have autocorrelation at lag 1 for MA1. You can only have autocorrelation at lag 1 and 2 for MA2. You can only have autocorrelation for lag 1, lag 2, and lag 3 for MA3. But if you're talking about MA of order 3 now, okay, what is the autocorrelation at lag 4? 0 and above. They're going to be 0. The autocorrelation for MA cut off at a particular lag. But for the autoregressive model, what cut off? Partial autocorrelation cut off. Please take notes. Okay. Now, we're still focusing on MA1. Now, how do we derive the mean and the variance of the MA1? Is what I want to show you now. Okay, the mean and the variance. You know, this is what I'm trying to say. You know, how do we know under the property here that the theoretical mean is going to be mu? How do we know, like if I have a YT, if YT follow moving average model of order 1, how do we actually know that the expectation of YT is going to be mu? And how do we know that the variance of, you know, how do we know the variance of YT is basically going to be sigma squared W into 1 plus A1 squared? And how do we know that the autocorrelation at lag 1 is basically going to be 1 divided by 1 plus A1 squared? Okay, we actually want to review what happened behind the scene, what led us to all of this. Okay, now that is what we want to do now. We actually, you have a MA of order 1, and we want to derive the mean and the variance. You know, like in exam, let's say you are given this. YT equal to 2 plus WT minus 0.8 WT minus 1. That's a MA of order 1. Why is the MA of order 1? You are relating the current value of the time series to the current shock and the immediate past shock that I call the current and the past immediate past white noises. Take a look at that. And you're giving the WT to be, WT is a white noise, actually follow normal with a mean of 0. And the variance of the white noise is basically 0.025. Okay. Now, how do you derive the mean for that? Okay. Now, take a look at that. Expectation, I'm going to introduce expectation to both sides, right? Expectation into 2 plus WT minus that. Okay, the expectation of a 2 is going to be 2. 2 is a constant. Then I'm going to have expected value of WT and expected value of WT minus 1. Okay, what is the expected value of WT? Can somebody tell me? What is the expected value of WT? WT is a white noise. What is the expected value? 0. Okay, somebody online says 0, right? Look at me. Good job. Send me a message for extra credit. Okay, send me a message for extra credit. Okay, the expected value of WT equal to 0. Look at that. WT, if you take a look at this guy now, look at what they gave you. Look at the specification. WT followed normal distribution with a mean of 0. Expected mean of 0 means expectation of WT. Does that make sense? And let me tell you this. Expectation of WT equal to 0, not only the current residual, even the previous residual, their expectation is 0. So expectation of WT equal to 0, expectation of WT minus 1 equal to 0. What do I have in the end? I'm actually going to have 2. Okay, so therefore, the expected value of YT equal to 2. Any question? Okay, so the value of YT equal to 2. Does that make sense? Okay. Now, how do we now get a variance, which is mu? Okay, mu equal to 2. Now, how do we now get the variance? We want to get the variance now. The variance of YT, that will be variance into that, right? Okay, now you can see we got a 2 that is a constant, right? Okay, so when we're looking at the variance is just going to disregard the constant, right? Because the variance of a constant is zero. You know, a constant doesn't change. Or that equal to that, right? Now, if that equal to that, then what we're going to do now, we're going to apply the law in statistics. So we're going to have the variance of WT, okay, minus the variance, okay, of plus the variance into negative is 0.8 WT minus 1, and that will automatically okay, lead to what I have now. Now I need you to take a look at this, okay, and see, I said the variance of WT plus the variance into negative is 0.8 into WT minus 1. Does that make sense? Okay, the variance of X minus Y in statistics, variance of X plus the variance into negative Y. Okay, if X and Y are independent, there's not going to be covariance. So right now, we're assuming WT and WT minus 1 are independent, then the covariance is going to be 0. So we're not going to talk about covariance. Now, if a constant is coming out of a variance, it's going to be a squared, right? That was why this guy is a squared. Then the variance of WT minus 1. Now, I want to award another extra credit. Now, can somebody tell me what is the variance of WT and what is the variance of WT minus 1? Don't forget, the WT is the current white noise. WT minus 1 is immediate past white noise. Can somebody tell me for a second? Go ahead. Is 0.25. Thank you so much. That is it. The variance of WT is that is what you see. So always make sure you pay your attention to the specification of the distribution of the WT. Okay. So when you have that now, you now gonna plug in 0.25 for both, because the variance of WT, the same thing as variance of WT minus 1. Okay, they're all going to be the same. Okay, in the end, okay, that we got something that look like that, and which is basically going to be giving you the idea of the formula. Like for instance, if you want to apply, this is how they deduce that formula. If you take a look at this guy now, that is the formula. That is the direct formula. How do we deduce the formula? From that expression, you have a 0.25 into 1 plus 0.64. What is a 0.25? A 0.25 is the variance of the white noise. Then into 1 plus is 0.64. What is 0.64 is when you square negative is 0.8. And negative is 0.8 is actually A1. Do you see that? So instead of you to go through all this, okay, they ask you to figure out what is the variance of YT. You just make use of sigma squared W into 1 plus A1 squared. All you just need to do is to plug in the variance of the white noise, and you plug in A1. You're done. That's all you mean. Okay, that's all you mean. That's super easy, right? Okay, now we now want to talk about the autocorrelation. Don't forget, there are three important things, right? The variance, the mean, the variance, and the autocorrelation, right? Okay, the autocorrelation now, of course, what is the correlation formula? Okay, the correlation formula between two variables is just going to be the ratio of the covariance, right? The ratio of the covariance. You take a look at this guy now. The ratio of the covariance divided by the square root of the variance of the square root of the variance of this, variance of that. And right now, I want to figure out the row 1. With MA1, I can only find row 1. For MA1, row 2 and above is going to be 0. Okay? Now, so covariance between YT and YT minus 1, take a look at that. You have a YT equal to that, okay, and YT minus 1 equal to that. From the YT, okay, if you take a look at this, if you take a look at this guy now, if this is YT, then this is automatically YT minus 1. Okay, you can deduce that from that. Just subtract 1. Or you have that. If you now want to find for the, let's handle the numerator first. The covariance between YT and YT minus 1. So, here now, okay, you are using this information, then you plug them in here. You see now, you plug them in. When you plug them in now, you now want to find what is the covariance of that guy now. Okay, that is basically going to lead, okay, when you take a look at this guy, that we're going to find ourselves here. Okay, we don't want a situation where we have a WT minus 1 because they are independent. That will be 0. That's going to go away. Now you have this guy now. Okay, now when you have, the only thing that go away there from the 2 is mu. Mu is a constant. Okay, so covariance is more or less like variation between two stuff. So the mu is going to go away because it's a constant. Then you have that. So you're going to see that what is eliminated is just mu. Now from here now, what we're actually going to do, you now start multiplying. WT times WT minus 1, that will be 0. Okay, by the time you do all of that, then you're going to arrive at only this guy. And that is going to leave you to A1 variance of WT minus 1. And WT minus 1 is the same thing as WT. It's the same thing as the variance of WT. So which is basically this guy. This is the covariance now. Okay, now if this is the covariance now, don't forget, we've already derived the variance the other time. Okay, the variance that we derived the other time, okay, the variance of, we need this guy now, right? Okay, the other time, if I go back, okay, this is the variance, right, for each, right? If you take a look at that, that is the variance of YT. Okay, if that is the variance of YT, that is also going to be the variance of YT minus 1. So which is this guy here. If you multiply and find the square, you're still going to have that. Okay, so now you now do this guy. Let me clean now. You now do this guy divided, okay, by this guy. You see that? When you divide, what is going to happen? The sigma square W will cancel out. And you're going to have this one, A1 over 1 plus A1 squared. Okay, so take a look at that. That's what you're going to have. Okay, now I want to move now. So that is how you can also go all the way. But if you try this, where will you find yourself? I'm afraid you're going to find yourself in 0, because for MA1, autocorrelation at a lag greater than 1, they will all be 0, because the MA will cut off. For the autocorrelation at lag greater than the one you are considering, the MA is going to cut off. Okay, so which is why you have this guy now. Okay, so if you now want to generalize and look at it properly, this is what we have. Okay, this is the generalization now. Like if I have for MA of order Q, okay, we can look at the MA of order 1 and make an induction for the MA of order Q. Okay, if the variance for the other one stop at sigma square W, if that one stop at here, then I can further extend that if I'm generalizing the order of the MA to all of these. Take a look at that. Okay, now if that is what I have now, okay, then of course I told you the other time the variance of YT would be greater than WT, the variance of that. And don't also forget autocorrelation, I said, are equal to 0 after lag Q for MA. If I'm considering MA of order Q, after lag Q, the autocorrelation will be equal to 0. Okay, don't forget. Okay, and let me tell you this. MA modules are always stationary. But you remember when for the autoregressive, they are not always stationary. You remember with difference, right? That was what we did yesterday, right? But for the MA, naturally, MA are generally stationary. You don't need to worry, okay? They are generally stationary, okay? Now, I now want to have a review. How do we identify an ARO of order P? And how do we identify an MA of order Q? Now, I want to go back now to what we've done before. To identify AR of order P, how do I know this particular data set requires that I should use autoregressive model when the autocorrelation function plot decreases as as lag increases, and when the partial autocorrelation function cuts off. That is the MA. I mean, that is the AR rather. Does that make sense? So for AR, okay, the autocorrelation decay exponentially as lag increases, and the PACF plot, okay, of the estimated autocorrelation will cut off at a lag P. Now, this is it. This is the ACF plot, and this is the partial autocorrelation plot. Take a look at that. Okay, you can see now, like PACF value here actually cut off at lag 1, not at lag 0, at lag 1. Okay, so you can take a look at that. Now, if that is what I have, okay, and an ARO of order 1, because of that, we say ARO of order 1 is appropriate. But what about MA? Let's go into MA now. Okay, look at the MA. Okay, you can see the reverse is the case. For the MA, PACF plot is the one that decay exponentially to 0. But for the AR, what decay exponentially to 0 is autocorrelation function. Does that make sense? In MA, ACF cuts off after lag Q, if you are considering MA of order Q. But what cut off after lag P in the AR model was actually the partial autocorrelation function plot. So take a look at that. Okay, you see now, when you see an ACF like that, that is an ACF plot for MA. That is the way it's going to look like. The ACF plot for MA model will cut off after that particular lag. And I need you to take a look at what I have now for the PACF. The PACF is anytime you see a PACF looking like this, you can look like this, like turning upside down, right? Okay, when you see a PACF looking like this and it's decaying exponentially to 0, then you are in MA. Does that make sense? Please take notes. Okay, MA of order 1 is appropriate for this time. So like you generate the ACF plot and the PACF plot for a particular time series data, and this is what you have, then you should be suspecting MA1. But if you do this, if you generated this, and this is what you see, you should be suspecting AR1. Okay, I'm trying to distinguish between the AR1 and the MA1 using the ACF and the PACF plots. Okay, we want to have I walk you through how to simulate under the autoregressive model, right? How to simulate ARO of order 1, how to simulate data set from ARO of order 2. Can we also do the same for MA of order 1? What is going to be the ARO code? My TA is going to walk you through all of that in the lab on Friday. I've already sent the materials to my TA. Now, we want to see if I want to simulate data set, from MA1, okay, take a look at this MA1 now. This is the code, okay? This is the code. What is missing here? Okay, what is missing? Okay, you actually going to specify the MA values. Okay, you're going to specify the MA values. Okay, the MA values, like this guy. Okay, this guy is going to be here, and what is going to be here? 6. 6 is going to be here. Does that make sense? 6 is going to be there. And why do I say SZ equal to 1? Because I look at the specification of a white noise here. Okay, it follows standardized normal distribution with the mean 0, the variance 1. When the variance equal to 1, the standard deviation is going to be equal to 1 as well. Okay, so that will complete all of that. Then by the time you simulate your data set, now you want to simulate 2000 data set. You can now, what do I want to find here? I want to find sample mean, sample variance, the same thing that we did under the AR model. We derive the theoretical mean, the theoretical variance, the theoretical autocorrelation. Then from the data set, we obtain the sample mean, sample variance, sample autocorrelation. We are doing the same now. Today, I just walk you through how to derive the mean of YT that follow MA of order 1, the variance of the YT, and as well as the autocorrelation. Okay, and right now we simulate a data set. Okay, I show you a code to simulate data set from MA of order 1, and from the data set you can figure out the sample mean and the sample variance, and you can compare your sample mean with the theoretical mean. You can compare your sample variance with the theoretical variance, just like the same thing that we did, under the autoregressive model. That's exactly what we're repeating now. Okay, so now if you want to compare now, according to the population model here, the mean is 6, right? Now, what was the sample mean? Very close to 6. You see that? Very close to 6. Okay, you can also figure out the variance too. Okay, I think the variance that we got was the theoretical variance of 1.64. But what is the sample variance now? 1.732. So this is going to enable you to compare, the sample estimate with the population one. Any question? Super easy, right? Now you can identify the appropriate time series model based on the ACF plot and the PACF plots. Okay, what is going to dominate the final? Okay, it's going to be stuff like this. You are given this, and it's okay. What kind of time series model is actually that? Okay, you see a ACF plot, okay, and you see a PACF plot, okay, and this ACF plot, what is it? Can somebody tell me what is it suggesting? What is it suggesting? Exactly, because the ACF. Do you see MA1? Yeah, MA1, because I see the first one is for 0. They say, yeah, MA1, it cut off after like 1. You're right. Okay, and you can see the PACF, we can give you stuff like that. Okay, now, so that is it. That's MA1 that you said. Now, for learning purpose, I will fit a model to the time series data if I already know the population model, just like what we did the other time. We simulated data from ARO of order 1 and order 2, and we confront the data set with the model again, right? So right now, I show you the code to simulate from MA of order 1, right? We basically want to simulate from, this is the code. I'm gonna you gotta see the code here. Okay, now let's say we already have our data set. Okay, we already have our data set, and let's say the data set is Y, and we want to estimate, we want to confront that data set with the MA of order 1. Now pay attention to this. For AR of order 1, it was 100. For MA, because it's going to be this, look at this. There's something that we call ARI, AARIMA. Okay, is divided into 3. AR, I, and MA, where this is going to have order P. Okay, this is going to have order D, and this is going to have order Q. If I'm focusing on MA, that means I'm not interested in AR, and I'm not interested in differencing. It's going to be 001. Does that make sense? But for the AR1, it's going to be 100. Okay, so take a look at what I have right now. Okay, now when I actually run the model, this is what I got. Okay, and from this is my feeder module. Do you see my feeder module, right? What is a mu cap? Don't forget, I told you the mu cap is always going to be the intercept. Okay, that's a mu cap, right? That's what you plug in, right? Okay, what is the A1? The A1 is this guy here. We approximate to 2 decimal. That was why you have 0.80. This is a fitted MA1 model. Okay, take a look at that. This will enable you to compare, okay, with the theoretical values. Take a look at that. Okay, now that is a feeder model. Now, if this is a feeder model, we can actually test. We can subject the model to diagnostic testing by doing what? Before we make a prediction, okay, you can subject the model to diagnostic testing, trying to look at the autocorrelation, function of residual and the like that we always do. But you know what? Let's say I want to make a prediction with it. I'm just going to write ARIMA, Y, or that 001. Here now, I want to predict for 3 ahead, like for 2001. Maybe my data set, don't forget, the data set we use is sample size 2000. Stop at number 2000. And I want to predict for the next 3, 2001, 2002, 2003. That is why I'm putting ahead 3. You see that? And what can you see now? These are the prediction value for 2001, for 2002, for 2003. Do you see that? So this is using R to make a prediction within MA of order 1. Okay, that is using R. Okay, and if you want to make use of the module, if you want to do it manually, this is doing it manually. But if you want to do it manually, don't forget this is your feeder module, right? That's your feeder module, right? Okay, if I want to get YT, if T equal to 2001, what is 2001 minus 1? That would be 2000. It means you need the residual for 2000. So you can get the residual for 2000 now using that mode or $ residual 2000. Okay, then you're going to plug that in. You're going to have your predicted value. If you want to do the same, you want to do for 2002, okay, I will leave you to determine this. What is going to be this? What is going to be the code you're going to specify here? Because here you're going to be needing what? The residual for 2001 and the residual for 2002. Okay, but you can see what I specified here, right? Okay, so this is doing it manually. Okay, like I said, you can do it using our code. Super easy, right? Super easy. Take a look at that. Okay, give me 1 second. Okay, now identify, we can give you more of that. Identify what the model is. When you see the ACF cutoff after lag 2, when ACF cutoff, it's MA2, right? And the partial autocorrelation function will actually behave like that. So take note. Okay, now this is like constructing the ACF plot and the PACF plot for that same set of data that we simulated from MA of order 2 or MA of order 2. Okay, so this is what you have. Take a look at that. Okay, and finally, you have, this is a model. Okay, for MA of order 2. Okay, here the 12 is the mean. Okay, so this is a model. What I'm just trying to tell the world is just that, I use this to simulate my data. And after simulating my data, I simulated 2000 data. And when I generate the ACF plot, it look like this. Generating the PACF plot look like that. That's why it is not surprising. Because initially, my data set actually come from MA2 model. Okay, so that's why it's not surprising. Okay, finally, you have, this is the model that we used to generate, and this is the code. Okay, if this is the code, of course, you can actually tell what is missing here. You know what you can put here, right? 2 values, 0.8 and negative is 0.2, comma. You're gonna come here. You are simulating from MA of order 2. And right here, it's gonna be 12, right? Then when you get your data, you can get a time series plot. You can get the ACF, you can get the PSEM. Does that make sense? All this my TA is going to walk you through in the lab on Friday. Any question before I go today? That's going to be the you know the light for today. Any question? Any question
Thank you.
before we go? Go ahead. Oh, do
I
you
was
want to ask
just
question?
saying thank you.
Oh, okay. Thank you too. Thank you too. Okay. Make sure you all stay safe and have a lovely day. But for now, everyone,